So good afternoon and welcome everyone to today's European Nuclear Society online webinar. My name is Omal Jawadana. I am a Senior Strategy Advisor at Sellafield Limited based in the UK and also part of the European Nuclear Society Young Generation Network board. It's my pleasure to host today's session today on a topic that's increasingly important for nuclear operators across Europe and worldwide, the remediation of damaged fuel, spent fuel rods for long-term dry storage. Our speaker today is Carl-Georges Plum, who's been working incredibly closely in the development and deployment of this technology at Framatome. He'll guide us through the technical approach, the lessons learned, and the values this brings to operators preparing for long-term storage or plant end of life. I'd like to say just thank you all for joining us. Please feel free to submit your questions through the chat and we'll address them during the Q&A at the end. This session is also being recorded as well, so we'll be releasing that recording afterwards if anyone wants to share with their colleagues and their networks who couldn't make it today. And with that, I'd just like to hand over to Carl to begin the presentation.
Well, fantastic. Thank you, Omar, and thank you, ENS, for making this happen. Yeah, let's get started. Hello, everyone. My name is Carl. I'm part of Framatome's fuel service team. And in particular, I'm heading the encapsulation team. And yeah, in the next roundabout 30, maybe 40 minutes, I would like to talk about what I do, what we do, which is remediation of defective spent fuel rods so that they become suitable for long-term dry storage. And yeah, let's jump right in. My goal today is to give you a brief overview on the topics of defective fuel rods. I don't know your background, but yeah, just to make sure everybody's on the same page. Then talk about our encapsulation technology and what we do to remediate these defective fuel rods, and yeah, finally our experience, our use cases, and yeah, then eventually in around about 30 minutes from now, I will wrap it up. Just quickly before I dive into the actual topic, I'm part of Framatome's fuel service department, and what we do and what we have been doing for decades really is working with irradiated nuclear fuel. We start from the very beginning where we design our own tools in compliance with the relevant norms that we need to fulfill. We build them, we test them, and once our customers and we are satisfied, we bring these tools to nuclear plants all over the world really, and yeah, do all kinds of fuel service projects, which have been 2,000 in the last 2 decades. Overall, our team is made up of around about 180 people. We're based in France, the US, and Germany, and the services we deliver really encompass the whole life cycle of a plant, starting with the new build, of course, during the operation of the reactor, and then finally at the end of the life, during decommissioning or potentially during restart operations. You might be wondering what it is exactly that we do, what our services typically are. And yeah, this typically comprises fuel deliveries, services kind of related around ascertaining the state of fuel, for example, visual inspections, but also measurements, sampling, or leaker detection. And yeah, beyond that, we also repair damaged fuel assemblies, and finally, we encapsulate damaged and perform encapsulation on damaged fuel. So we remediate in a way that it can continue its way along the fuel cycle. And of all these activities that we do, I'm in the encapsulation part, and this is what I want to talk about with you today. So yeah, right here you can see what a damaged nuclear fuel rod looks like. This particular rod has breached cladding. We cannot see exactly what caused this damage, but we know from the damage we see that it was caused by debris fretting. So it could have been something as mundane really as a metal shaving or a piece of wire grinding against the fuel rod when it is in the reactor. So yeah, now you have a damaged fuel rod, by defective fuel rod, and the definition of defective is not straightforward. Ultimately, it depends somewhat on the functions that you expect your fuel rod to fulfill. And this in turn depends on where you are in the fuel cycle and also on your regulatory environment. For example, a fuel rod with a hairline crack might be considered damaged when you talk about using it for another cycle. But depending on your regulatory environment, it might be perfectly fine to put this particular fuel rod in a dry storage cask. However, to not complicate things, typically a damaged fuel rod or a defective fuel rod is a leaking fuel rod with some sort of cladding breach that comprises damages the containment of the radioactive material. Also potentially a fuel rod that is no longer intact, that is in pieces. And here ultimately these damaged fuel rods these leaking fuel rods cannot function as required for post-reactor operations, which gives rise to the need to solve this issue somehow. Just to put this into context, the good news is that the rate of leaking fuel rods has reduced by 10 to 20x in the last decades. It used to be somewhere around 150 to 200 leakers at the end of the 80s, and now we are 150 to 200 liters per million fuel rods at the end of the 80s. And now we are sitting at somewhere around 10 to 20. And yeah, this is really a major achievement, which was driven by improved manufacturing and design experience, but also by increased operating experience with the current nuclear fleet. And yeah, everything taken together, we estimate that at least in Europe, there are around about 1,000 failed fuel rods sitting in ponds all over Europe, and yeah, across the world, of course, a lot more. Just to illustrate this issue of defective fuel rods, this is how the problem arising from defective fuel rods looks when you see it in the context of the nuclear fuel cycle. Basically, your fuel comes from the reactor. It goes to the spent fuel storage. You realize that you have a defective fuel rod, you have a leaking fuel rod. And as a result, your access to long-term dry storage and or final disposal is blocked. So that means if you are an operator, you need to address this issue, because sooner or later you will want to get these fuel rods out of your pool. And what is typically done to manage this is that defective fuel rods are identified within the fuel assembly. They are pulled from the fuel assembly. They are removed from the fuel assembly. Afterwards, they are stored inside the pool in sleeves or potentially interim canisters to enable batch treatment at the end of life of the plant, which is because they're not considered permissible content for dry storage. IAEA and most regulators say that in order to, again, turn them into permissible content, some sort of remediation of the damage is required. And this is always with the ultimate goal of enabling this fuel to enter the fuel cycle again. And this brings me to the real topic of today's webinar, which is encapsulation. That is Framatome's, our technology for dealing with defective fuel rods. And I was thinking about how could I best explain you the challenge that goes into remediation. And yeah, I realized it's a bit like an onion. In order to remediate the damage, you want to reestablish radiological confinement. In order to reestablish radiological confinement, you want to create a new long-term barrier. So to replace the first barrier that was damaged. This confinement, ideally, you want it to be a welded confinement, a welded containment. However, before you can put it into this containment, you need to dry it. And not only do you need to dry it, you also need to prove the dryness beyond any doubt. And after drying and welding, you also need to prove the weld quality that you have produced. And yeah, finally, all this has to happen inside the spent fuel pool, since we're always talking about highly radioactive irradiated fuel. The answer we came up with in order to deal with these challenges is our encapsulation process, which is used for encapsulating these defective fuel rods. Basically, what happens there is that we take a defective fuel rod, we perform what we call pre-treatment. More on that on the next slide. So we perform pre-treatment. We put the defective fuel rod into a fuel rod capsule, which will become the new first barrier. This fuel rod capsule will then move in the next step into our encapsulation facility, which is sitting at the bottom of the pool. Inside this encapsulation facility, the fuel will be dried, the fuel will be welded, and also ultimately tested. And finally, once the capsule has been finished, has passed all the tests, the capsule can be placed inside what we call a capsule canister in step number 4. And this capsule canister pretty much handles like a fuel assembly and can then be placed in a transport or storage cask, which then can ultimately go to dry storage. So this is the big global overview of what our encapsulation process entails. And yeah, I want to share with you a little bit more of the details, how this actually works and what we do. We always start by drilling a hole into the plenum of the fuel rod. You will be wondering at this point, why are they drilling a hole into the plenum? That's not something you would usually do. However, for our encapsulation process, this creates a defined opening size, and through this opening size, we dry the inside of the fuel rod that is potentially has some moisture too. This drilling unit, you can see the unit here on the pictures. The interesting and the complicated part of this really was designing a system that extracts the fission gases as well as the cuttings as you're drilling into the fuel rod, which is what we do. So once we have taken the defective fuel rod, we've drilled a hole in the plenum, and we take it out of the drilling unit again and put it into one of our capsules. The capsule then goes into what we call the encapsulation facility, which you can see here on the pictures and which is really the heart of our equipment. The encapsulation facility, as you can see, is modular, so you can adjust it to the length of the fuel rod and to the requirements of different plants. And this facility contains all the equipment that is needed to dry the fuel rod, to weld the fuel rod, to prove the quality, to prove the dryness, and to prove the quality of the weld. By the time the fuel rod leaves the encapsulation facility, it is good to go into a capsule canister and ultimately into a dry storage cask. A central part of the process that happens in our encapsulation facility is the drying process. The drying process is crucial so that there is no moisture left inside the fuel rod and or the capsule, which could potentially create hydrogens through radiolysis. And what we do in order to dry the fuel rod is circulating heated inert gas through this capsule with the fuel rod inside while we're heating the capsule. We do this for a defined amount of time, and eventually we stop the circulation, we shut in the pressure, and we monitor how the pressure inside the capsule is behaving. The heating stays on at this point, and if there is a rise in pressure, that would indicate that water has evaporated, and as a result, it has not been completely dried yet. And if that is the case, we go for another cycle of drying until we can prove that this fuel rod is dried to the requirements that we need to meet. And we put a lot of development into this process, and into proving that we can dry fuel rods even at fairly high burn-ups, and as a result, fairly low permeabilities inside the fuel rods. But even there, we have proven that we can dry the fuel rods to regulators. So once the drying process is completed, once the dryness has been proven, we close the end plugs on the capsule and move to the next part of our process, which is the welding. Unfortunately, I could find a video for you that shows how it looks. So all that you're seeing here is happening at the bottom of the pool. It's all remotely controlled. Basically, this is an orbital welding process that moves around and creates this weld and really finalizes seals the first barrier that we are creating here. There we go. A little bit more on welding. Since the capsule has two end plugs, top and the bottom, we are welding it twice. We have a welding unit at the bottom, in the bottom housing, and again on the top. The welding unit during normal operation is somewhat at a distance from the fuel rod, and only at the time that we want to weld, we can move the welding system towards the capsule and create this weld. The key here really was to develop, and the challenge really was to develop a process that is highly automated and always produces the same reliable quality of weld, which is what we're doing here, what we have achieved after a lot of testing. So now we have dried the fuel rod, we have welded the fuel rod, and we have dried the capsule with the fuel rod, we have welded the capsule with the fuel rod inside, and eventually we arrive at what I would call our final product, which is the capsule that serves as a new long-term barrier for the defective fuel rod on the inside. You can see in the picture here on the left that the defective fuel rod is here inside the capsule, and it is held in place by filling pieces to keep the fuel rod from really moving around inside the capsule. And this capsule is then taken and placed into what we call a capsule container here on the right, which holds 35 capsules and can be placed in a dry storage cask, just like a fuel assembly. You might be having a few questions now that you've seen or you got a first impression of our system. The first question might be why are we using a welded confinement versus a screwed confinement? For us, ultimately, the reason why we decided to go with welded is that we can achieve a greater degree of tightness. We have a wider coverage of regulatory environments around the world, really, and we also have better corrosion resistance properties. The next thing you might be wondering is why are we using individual capsules rather than one big quiver where all the capsules go inside and it's only welded or screwed once. And for us, the reason to use individual capsules, again, is to really recreate the first barrier to the greatest possible extent, which is what we're doing with individual capsules. They also allow us to prove the dryness and the weld quality of every fuel rod by itself. And ultimately, we consider this a risk reduction measure. The principle here being that we don't want to put all our eggs in the same basket. If there were to be a situation where a weld is not according to requirements, one would only have to open one capsule and move one fuel rod rather than however many are in your quiver. The next question some of you might have been wondering about is why are we using hot inert gas rather than vacuum drying, since vacuum drying is commonly used with dry storage casks. And the reason is that in our analysis of the process, we realized that vacuum drying cannot reliably meet the dryness criteria we need to fulfill under all circumstances. That is because, other than when you have a dry storage cask where the fuel rods are intact, we are dealing with defective fuel rods that do have moisture or water on the inside, and we also want to be able to dry the inside to evaporate that water, and this is what we can do with our process, which vacuum drying cannot in all situations. And then finally, why are we doing it underwater versus next to the pool? It's also not a lot of thought and design also went into this. Ultimately, we decided to go with this particular solution Because we're dealing with radioactive irradiated fuel, so there's a greater radiological protection if we have the facility underwater for our people and colleagues. And the other advantage is that we can place our encapsulation facility in the same area that is usually occupied by the dry storage casks. So we can ensure compatibility with most plants. Basically, if the dry storage cask fits in there, our encapsulation facility will fit in there. So yeah, that's the theory of what we have been doing, of our design of our system, but of course there's also our experience and practice. First of all, the use cases, like when we use encapsulation, what makes sense? And so far there are two use cases. And typically, and what we have been doing so far, is the end of life scenario, where defective fuel rods accumulate, or defective fuel assemblies accumulate in the pool, probably over decades. Eventually they are repaired at the end of the lifetime of the plant, and all the fuel rods are capsuled in one big campaign after the shutdown of the plant. The other use case, which potentially has some advantages, know that this technology exists, is to already have a capsule canister and capsules present in the pool during the lifetime of the plant. And whenever there's a damaged fuel rod, that fuel rod is extracted from the fuel assembly and already placed inside a capsule, which ensures safe containment of this defective fuel rod for however much remains of the lifetime of the plant. And potentially during the lifetime or after the end of life, we come again with our facility and encapsulate all these capsules that are hopefully waiting for us at this point. Yeah, with some experience with what we're doing, this is not a paper technology, as you have probably guessed from the pictures. The development started originally in 2014 in the context of the German nuclear phase out. And since 2017, we have been working with this equipment in the field. So far, we have completed a total of 4 campaigns on fuel rods of 12 feet and 14-foot lengths. From our experience so far, we take approximately 1 day for treating 1 fuel rod. So going through the whole encapsulation cycle takes round about 1 day. So it's critical for us, for our system, that we can operate around the clock. Additional time will be needed for the pre-treatment of the fuel, which is putting it into the capsules, the drilling and putting it into the capsules. Additional time will also be needed for the assembly and the dismantling and the decontamination at the end. It's somewhat hard for me to give you a good estimate at this point, since it really depends on the plant and on the requirements of the plant, how long that might take. And since we have been doing this for a few years already, and since we did a few campaigns, we made some experience, we learned our lessons, and implemented improvements to our process and to our facility over time. And chiefly among this improvement is an optimized heating process, which is something that we are working on at the moment. But not only that, we also worked on made changes to the tool that we use to transfer the capsules with the fuel rods into our facility. And beyond that, we have also been regularly updating our procedures to incorporate the experience we've made in the field. So the message I'm really trying to convey here is that this technology is mature and proven. It has been around for a few years. We have done it 4 times. We have learned some lessons. We made improvements, and we have the people that know how to use it. One more remark here on the compatibility. When we designed the system, we put a lot of emphasis on modular design to ensure compatibility to different plants, which is why we designed it to have the same dimensions as a storage cask. Mentioned briefly before, ultimately, wherever you can fit a dry storage cask, for your fuel rods, you can fit the encapsulation facility. The encapsulation facility itself is adaptable to different fuel rod lengths as well as the diameters. And yeah, finally, our product, the capsule canister that contains the 35 capsules, has the same geometry and handles like a fuel assembly. So it is compatible with the existing equipment at the plant. So yeah, last but not least, I would like to wrap it up. The 3 key points I would say are the key takeaways for today. First of all, that defective fuel rods, leaking fuel rods require some sort of remediation before they become suitable for long-term dry storage. How exactly that looks will depend a little bit on the regulatory environment where you are, but something will need to be done. Secondly, the first barrier that has been damaged, that is defective, can be reestablished with our encapsulation process. And everything, all the drying, all the welding is done inside the pool in our encapsulation facility. And yeah, last but not least, encapsulation is a mature technology that has gone through multiple campaigns since 2017. And yeah, this brings me soon to an end. Thank you all very much for attending. Thank you for your interest in this topic. I'm curious to hear your questions, and should there be any questions that we cannot answer today, or maybe you don't get to have your questions anymore, feel free to get in touch. Feel free to write me an email if you want to discuss further about this topic. And yeah, with this, I hand it back to Omar. Thank you, Omar, and thank you, ENS, for making this possible.
Thank you, Carl. It was a really, really interesting presentation. I know there's been a lot of discussion in the chat with lots of different questions. So I've picked out a couple of them. So yeah, like Carl said, if we don't get around to all of your questions, please feel free to get in touch. But firstly, I'll start with one of my own questions. So in the pre-treatment stage, what sort of measures are taking place to control the release of radioactive particles during the drilling operations?
That is a good question. Let's see, let me go back to the equipment, to our drilling unit. Basically, the drilling unit has a suction system that is connected to the exhaust of the plant. It has 2 suction systems, in fact. It has one suction system for fissile gases that is connected to the exhaust of the plant, and it is operating the entire time as we are drilling to catch all the all the gases, the release of gases, which you can see on the camera as you're drilling. The other suction system is related to the fissile, to the cuttings that you create while you're drilling. And yeah, there's usually some equipment at the plants, or there's some suitable equipment that we use to suck these cuttings into a filter. I hope this answers your question.
Yes. Yeah, thank you. I'll take a couple of the questions. I've been noting some of them down from the chat now. So this is sort of on a similar vein to my question, but it's during the encapsulation phase. Do you consider the possibility of fuel fragmentation and the release of UO2 particles from defective fuel rods into the capsule?
Okay, here we can see the capsule. The defective fuel rod itself is held in place in the capsule. If there's a situation where the defective fuel rod has been degraded to such an extent that it's really, or if it's in pieces, I'm not showing it in this presentation, but we also have what we call sleeves. These are basically kind of capsules inside a capsule. It's a small capsule, round about the diameter of a defective fuel rod. We can fill debris that could otherwise not be held with the filling pieces into this sleeve, and then we put the sleeve into the capsule like a defective fuel rod. So there's two options. You have a defective fuel rod that is good enough and has sufficient structural integrity to be held by the filling pieces, or you have small pieces and then you use what we call the sleeve, which will ensure the position of these defective fuel particles inside the capsule.
Yeah.
Does that make sense? Does that answer the question?
Yes, I think so. I think if there are any follow-ups to whoever's asking the questions, please drop it in chat or
maybe like in this context, now that we're looking at this picture, the top and the bottom plug of the defective fuel rods also have a filter inside, like a sintered metal filter. So any potential small fuel fragments that are inside the capsule will not leave the capsule during the drying process, so they don't end up in the drying system of the encapsulation facility.
Yeah. Thank you. I'll move on to another one of our questions from the chat. So there's been a few questions on the drying process. So I'll pick this one. Has it ever been witnessed that the inert drying gas cannot circulate from one end of the fuel rod to the other?
No. No, because the inert gas is not cycling through the fuel rod, it's cycling through the capsule. And there's always an annulus. The system is designed in a way that there's an annulus between the fuel rod on the inside and the capsule walls on the outside. And with our drying process, and we have proven this in hot cell tests, we don't need to circulate the helium actually through the fuel rod. We circulate it past the gas, the inert gas. We circulate it past the fuel rod, and this takes away the moisture.
Yeah.
And since the annulus is always, since the dimensions of the annulus are always there, we didn't have that issue.
Brilliant, no problem. Thanks. I'll move us on to our next question. Which physical processes represent the primary risks during storage of encapsulated defective fuel? Cladding embrittlement, capsule degradation, creep, or is it something else?
You're talking about the storage inside the pool or the storage in a dry storage cask? Or maybe both. I guess I can talk about both.
Let's talk about both. It depends on the who. If there's a person that asked this question wants to get specific, please drop it in chat. But yeah, we'll go with both.
Yeah, probably it's interesting to talk about both.
Yeah.
So when the damaged fuel rod is sitting inside the pool, there's always the topic of some radioactive contamination being released into the pool water, especially if you have it sitting inside a quiver, and if you're moving that quiver maybe up and down, the pressure changes could lead to the release of fissile gases from inside the fuel rods. As for degradation of the fuel rod inside the pool, to my knowledge and from what I hear from colleagues, from what we have observed, once to degrade further, the fuel rod really needs heat, it needs water, and it needs radiation. And when the fuel rod is sitting at the bottom of the spent fuel pool, all you have is water. So typically you don't see much more degradation once you're not in the reactor anymore. That at least is our experience. So yeah, that much about defective fuel rod sitting inside the pool in the water. Now about a defective fuel rod in a dry storage cask. Depending on where you are in the world and depending on the regulatory requirements, regulators have come to different conclusions what could happen and what exactly they demand from the operators as a consequence. The advantage of having this capsule is that you have your first barrier around your fuel completely restored, and you always have a well-defined position of the fuel. There's no risk of this fuel being anywhere other in the capsule, which is where it is allowed to be in accordance with your dry storage cask license. So yeah, I hope that answers the question.
Yes, thank you very much. I've actually got another question as well, just on that line. So, which countries are this system qualified in?
We have cask licenses, casks that are licensed to handle the ultimate product of our system in France and Belgium. So far, we worked with this system in Belgium. We did some testing with it in Switzerland, and yeah, it was developed in the wider context of the German nuclear phase-out. So I'd say Central Europe.
Okay, no problem. That's always good to know. I'll take another question from the chat now.
So many questions. That's great.
Yeah, so there's lots of questions. I'm trying to keep up with them. Does the protective guard on the capsule container provide the same or better rigidity of a spent fuel assembly, such that the capsule container provides the protection necessary against hypothetical accident conditions associated with transportation? It's very close up on the chat, so if you want to have a look and have a read of it, it's a long question.
At least it does provide at least the same protection and rigidity in case of accidental conditions that a fuel assembly provides. I know this because we had this discussion and we had to prove it as part of licensing dry storage casks to be able to hold this content. So I can tell you that it definitely fulfills the requirements of the dry storage casks for the different accidental conditions. I remember there was one related to temperature, to heat expansion. There was another one related to acceleration inside the dry storage cask, and we meet all these requirements. Oh, we did in the two legislations where we have it licensed, which are France and Belgium.
Brilliant. Thank you very much. We'll pick another question from the chat. I'll try and pick something a little bit Right. Okay, so do you have any more information on the hot cell tests that you've done? Anything you think would be interesting to share?
Oh, any more information? It's a very broad question.
Yeah.
I can tell you a tidbit, a little factoid that I thought was interesting when I talked with the people who designed these tests and built these tests. And yeah, they were telling me that the permeability of the fuel column inside the defective fuel rod, once it has been irradiated and has like certain burnup, is more comparable to concrete, or is like somewhere order of magnitude of concrete. So yeah, this is something I found interesting. And yeah, for these tests, I know that we argued and that we have proven that with our system, with the time that we're drying it, with the temperature we're drying it at, with the circulation of the inert gas, that we can remove all the residual moisture, even from a fuel rod that has such, yeah, where the fuel column has such low permeability.
Yeah.
I hope that is. I'm not sure if it
Yes.
answers the entire question. It was a very big question, but
It was a very big question. I think this one's a little bit more specific. So, what heating method do you use for DFRs since it needs to be underwater?
what heating? We have electrical heating in there. So there's we have somewhat multiple heating systems. On the one hand, we have electrical heaters in our facility that heat up this the defective fuel rod. Of course, there's appropriate insulation to ensure that we reach the required temperatures on the inside, and we do, of course, measure them and prove them as part of our process that we have reached them. And the second part of the heating is the heating for the gas itself. The inert gas is also heated before it goes through the capsule or into the capsule. Then it is dried, then it's heated again, then it goes back into the capsule. So yeah, these are the two systems that we have to bring heat, to bring temperature into the capsule and the defective fuel rod.
Yeah, that's thank you. So how do you test and confirm the tightness of the welds?
How we test the tightness of the welds? We, during the operation with actually irradiated fuel, we have two tests. First of all, we do a visual test of the weld with the cameras that we have in our facility. And secondly, we have an ultrasonic testing system that is specifically designed and developed for these welds and for these capsules to prove the integrity of the weld. And yeah, maybe in addition to that, it's interesting to know that before we start working with live fuel at every campaign, before we start encapsulating actual irradiated material, we do a test capsule, and this test capsule without irradiated material is taken out and we bring it to a lab to do some cross sections on the weld.
Okay.
And yeah, then depending on how many capsules there are to be encapsulated, every X capsules, we do that again. And then at the very end of our campaign, we do it one final time to prove that our system is still creating good welds.
No problem. Thank you very much. I've seen this next question coming up a couple of times. So what is the required temperature for the drying?
Oh, the required temperature for the drying. Typically 180 Celsius. For, in some individual cases, 190 Celsius. Whether or not this temperature ultimately yields a dry fuel rod and a dry capsule, this goes out. This is one parameter among many in our calculation, our drying design. For example, time being another big parameter. But yeah, 180 or 180 to 190 is the answer here.
Thank you very much. Yeah, we've got lots of questions still coming in, so I'll keep moving on to answer as many as we can. How do you take the defective fuel rod from the fuel assembly?
Oh, that is typically not part of our encapsulation campaigns. However, I have colleagues at all the fuel service departments in France, in the US, and in Germany, which do that. And yeah, they have systems that allow them to extract and experience to extract all kinds of damaged fuel rods that might just have a hairline crack that can potentially be pulled, and fuel rods that are far more damaged where more tailor-made repair solutions are needed.
Okay, yeah, thank you. Okay, let's move on. Another bit of a longer question again. What percentage of spent fuel rods are typically found with guillotine type fractures during the inspections? And is the encapsulation process similar for this?
Guillotine type fractures. I cannot tell you from the top of my head how I cannot put a number on that from the top of my head. As for the encapsulation process, it's similar. In some ways, it's even easier because if the fuel rod is already guillotined, if it's cut already, then we don't need to drill a hole into the plenum anymore.
Okay. Yeah.
And yeah. Otherwise, same procedure. If it is really in like small pieces, then it needs to go into one of our sleeves before it can go into the capsule. We have equipment, we have funnel to fill these sleeves with little fuel that is broken into pieces. And if it's a longer piece, then we can place it into capsule right away.
Yeah, no problem at all. So I suppose this is along a similar line. So what if the spent fuel rods are bent and not broken? Can it still be encapsulated? I suppose then you get a bit more of a fit issue, I guess.
No, that is an interesting question. We have not had that situation yet on how one could deal with such fuel rods. I mean, obviously, they're heavily bent. We cannot just stuff them into the capsule. A lot of answers would have to be found how to make these fuel rods suitable for a capsule. And we haven't had that situation yet.
Yep, that's no problem at all. It's an interesting thought, I guess. We've got another question. When you remove a fuel rod using different equipment, where is it usually stored before you encapsulate it, and what equipment is used to transport the fuel rod?
Where's it stored? Depending on the plant, depending on the country where you are, some have what they call interim canisters, which are like somewhat quivers, where they can place defective fuel rods that are permanently in the pool. Some plants have a capsule system, which is also something we do, that puts these fuel rods into capsules. The capsules are not dried and welded, so they are not suitable for long-term storage, but at least they are contained during the life of the plant, and the risk of additional contamination of the pool is lowered. So yeah, there's quivers, there's like encapsulating solutions that are not long-term storage. And yeah, the second part of the questions, how is the fuel rod moved? that depends on the state of the fuel rod. If you have a fuel rod that is very reliably structurally intact, again, also depending on which plant you are, what the exact requirements are, but there's typically a fuel rod gripper that either grips it at the top plug or a tool that pulls the entire fuel rod into the pool and into the tool and closes at the bottom. So if there were a failure of the top plug, this is held. It depends on what is needed. Both solutions have their advantages and disadvantages. And yeah, if the fuel does not have a top plug anymore, there are gripper systems that can handle the fuel once it has been pulled out. So then the fuel is gripped on the, yeah.
Brilliant, thank you. We're coming close to time now, so I'll ask one more question. If anyone's got any more questions, please drop them in the chat and we'll try and get round to them depending how quick this one is. So how are the capsules permissible for long-term dry storage?
How are the capsules permissible for long-term dry storage? Also a big question, but yeah, they are ultimately they are permissible because we argued as part of the cask license that they meet all the requirements in terms of integrity, in terms of behavior under heat, but also in terms of leak tightness, in terms of corrosion behavior. So we have all this proven and argued in reports. And yeah, this was then reviewed by the regulator in each country as part of the cask licensing process, and potentially also there's another review separately for the process itself, independent of the cask license.
Okay, yeah, thank you. I think we probably have time for one more question. So final question then, is it recommended that the encapsulation process is applied after a reactor is permanently shut down, or is the preference for it to be applied after defective fuel is identified, or is it just up to the utility?
The advantage when you're doing it, the advantage if you put fuel into capsules during the lifetime of the plant is that you reduce the handling steps with fuel. If you put your defective fuel rod, let's say you put it into a quiver, let it sit there for another 30 years until the end of the life of the plant, then you have to take it out again and put it into a capsule. Depending on how damaged the fuel rod is, you might really want to have as little handling steps as possible. And if you put the fuel directly, once you have taken it out of the damaged fuel rod, once it's out of the fuel assembly, and you put it directly into the capsule, you save a handling step. So that's one advantage of at least placing it in capsules during the lifetime of the plant.
That's brilliant, thank you. I think we're coming close to time. I'm seeing the questions are slowing down as well. So I'd probably bring us to a close here and say thank you for everyone for joining us. It's been a really interesting session. Thank you very much, Carl, and everyone at Framatome for putting on this presentation and talking to us about it, answering all of our questions. You've shared some real world experience from campaigns since 2017, and it's a really interesting presentation. So on behalf of ENS, thank you very much. I'd also like to say a big thank you to Mattia for organising this. It's been a really good presentation and a really good session. Yeah, if you have any questions, like Carl said, please do feel free to reach out. Hopefully see you at our next webinar. Until then, thank you very much and enjoy the rest of your day.